This video is going to look at the reactions of acyl chlorides. Now this is for A-level chemistry. Now you can see I've drawn an acyl chloride here. So the one I've drawn is ethanoyl chloride. So ethanoyl chloride. Now acyl chlorides are very important compounds, and you're going to do quite a lot of reactions with them in A-level chemistry. They are very, very reactive, and therefore they're really useful for making lots of different things. Now this example here, this is ethanoyl chloride because we have the CH3, so we have CH3 here and C here, so we have two carbons giving us the ethane part, and it's an oil chloride because of the COCl group at the end. Now this is a very, very reactive compound here. So we've got a strong polar charge between the carbon and the oxygen in this, which means that the acyl chlorides are very susceptible to attack by nucleophiles. So these are some of the reactions that we're going to have to look at in this video. First of all, however, we're going to look at how you actually make an acyl chloride. So to make an acyl chloride, you need to start off with a carboxylic acid. So to make ethanoyl chloride, we're going to start off with ethanoic acid. We're going to react it with sulfur dichloride oxide. This produces the ethanol chloride, our acyl chloride. There'll be sulfur dioxide and hydrogen chloride released as well. So this is our reaction for producing an acyl chloride, and these acyl chlorides are the things that we're looking at because they're very, very useful and they're very, very reactive because of the polarity of the CO group. Now, there are three different reactions that we need to look at for mechanisms. So we need to look at the reaction with ammonia, with alcohols, and with water. Now the reactions are all pretty much the same. The mechanisms are all the same, but I'll draw all of them so you've got an example of each one. So first of all, we'll start off with ethanoyl chloride, and we're going to react our ethanoyl chloride with water here. So we've got our polar group, with the oxygen being more electronegative than the carbon, drawing the electrons towards itself. And then we've got our water, which is going to add in, because water has the lone pairs of electrons, which allows it to act as a nucleophile in this reaction. So, to draw this, I'm going to use a red pen to show that there's a movement of a pair of electrons from the nucleophile to the positive carbon. That results in the electrons being repelled away in the double bond towards the oxygen. We end up with an intermediate where we have the pair of electrons on the oxygen that have been repelled away. We have a negative charge up here. We have the chlorine still attached, and now we have a water molecule attached to our acyl chloride here. We have a slight positive charge, we have a positive charge on the oxygen here. So our next step is to show how this intermediate then ends up forming the final product. So it won't last for long, it's just an intermediate. Now what happens is this lone pair of electrons here will go in to reform the double bond. The chlorine is removed, and then one of these hydrogens will cleave off as the electrons are attracted towards the positive charge in the bond. So we end up with our final molecule, or our final product, which is CH3, C, double bonded oxygen for this double bond here, and then we have an OH on the end of it. So we've produced a carboxylic acid from the acyl chloride. The other product of this reaction is the hydrogen chloride. So one of the hydrogens here that came off, and the chlorine here makes us some hydrogen chloride as well. So these are our two products of the reaction. In the next reaction, we're going to use ammonia as our nucleophile. So we have NH3 here with our lone pair of electrons. Again, we have a movement of a pair of electrons from the lone pair to the carbon, to the positively charged carbon. The electrons here will be repelled away towards the oxygen. The intermediate is going to look very similar this time. So our intermediate, we've got the CH3 here, the C, oxygen with the lone pair, the negative charge. The chlorine's still there in our intermediate, and we have ammonia attached as well. And as it was with water, there's going to be a positive charge on the nitrogen this time for our intermediate. The molecule will then collapse back in. The pair of electrons will reform the double bonds. The chlorine will cleave off, and then one of these hydrogens will be removed because we don't have more than 3 bonds for the nitrogens. We've got 1, 2, 3 bonds there. So then our product is going to have CH3 here, the double bonded oxygen that's formed, and then the NH2 on the end here. So our product this time is an amide. So we've got ethanamide as our product. Ethanamide for the amide group here. Now, an important part of this reaction is also the fact that we're going to produce the hydrogen chloride here. So we've got HCl as one of our products, along with the amide as well. Now, the reason why that's important is because I'll draw it here. With the HCl is an acid. We're reacting a base with it, so there's going to be an acid-base reaction between the hydrogen chloride and some of the ammonia that hasn't reacted at the start. So what we'll end up having is a side reaction which produces ammonium chloride because the ammonia and the HCl react together. So we end up having the NH3 reacting with the hydrogen chloride, and this makes NH4Cl. So this means initially we'll have white steamy fumes of HCl, but these steamy fumes will react with the ammonia in solution, and we'll end up producing a white smoke of ammonium chloride as well. In the previous reaction, I should have mentioned that the HCl would have come off as white steamy fumes as well. The third reaction, we'll look at the reaction between an acyl chloride and an alcohol. So sticking with the same theme, let's look at with ethanol. So it's CH3, CH2, OH. We've got the lone pair of electrons there on the oxygen. This pair of electrons, so the alcohol is going to be acting as our nucleophile here. We've got the lone pair of electrons attracted towards the carbon, the delta positive carbon. Electrons in the bond repelled away towards the oxygen. We are then going to have the intermediate here. So we've got CH3, we've got the negative oxygen here, the chlorine here, and then the alcohol group attached here. So that's CH2, CH3 there. Again, delta positive, again the positive oxygen here. So this intermediate is going to collapse back in. It's going to not last very long. So the electrons from the bond here attracted towards the positive charge. Electrons here reform the double bond, and then the chlorine is removed as well. And then we get our final product, which is going to be an ester. So we have CH3, C, double bonded oxygen there from the reformed bond. And then we have the ethyl group from the alcohol is added here. So there's our ethyl group. And then our other product is one of the hydrogens and the chlorine have come together to make hydrogen chloride. So you get steamy fumes of hydrogen chloride from this as well. So this is how you would actually form an ester from an acyl chloride. Now there's an advantage to this reaction. The main advantage is that you go to completion, so you will form, this reaction not being reversible means you definitely form your ester. You get a much higher yield of the product that you actually want. The other big advantage of this is because the acyl chloride is so reactive, you can perform this reaction at room temperature, and it's much faster. It doesn't require all the refluxing that you would need for forming an ester from a carboxylic acid and an alcohol. So it's a faster reaction with the acyl chloride and a higher yield of the product that you actually want. Okay, to summarise these reactions of acyl chlorides, what we've been looking at is the nucleophilic addition, elimination reactions. So for all of our reactions, we've had a nucleophile. So our nucleophile was ammonia with a lone pair of electrons. It was water with a lone pair of electrons on the oxygen. And it was also an alcohol with a lone pair of electrons on an oxygen as well. So the nucleophilic addition, we add it, and then we eliminate a small product. In most cases, we were eliminating hydrogen chloride. So nucleophilic addition elimination reactions of acyl chlorides. Now, I'm going to summarise all these different reactions now. So I'm going to write equations for the different reactions that we've actually done. So our first reaction with water, we had ethanoyl chloride reacting with water to make ethanoic acid and hydrogen chloride. So we added in our nucleophile and then we eliminated our hydrogen chloride, our small product. The second reaction that we looked at was our ethanol chloride, but this time we reacted it with ammonia. So we had NH3. We produced an amide from this. And then the other product was ammonium chloride as well. So we made ammonium chloride. So we need two of those for this reaction. So we made ammonium chloride because the ammonia reacted with some of the hydrogen chloride that was released and eliminated from the acyl chloride. The next reaction is looking at the alcohol, CH3COCl plus ethanol. So that's our nucleophile. These are all our nucleophiles. And here we make an ester. So ethyl ethanoate is our ester. And HCl is the eliminated product here. So these are all addition elimination reactions again. So we've added in the nucleophile and we've eliminated a small product on the other side. We can bring this all together and have a look at another reaction. So we could look at what happens when you have a primary amine, if you react a primary amine with an acyl chloride as well. So if we bring it all together, we have our acyl chloride, CH3COCl. We have our delta negative oxygen, delta positive carbon. This time we're going to react a primary amine. So our primary amine is going to be NH2, and we'll have a CH3 here. So we'll use methylamine with our lone pair of electrons here on the nitrogen. As with the other mechanisms, the lone pair of electrons is attracted towards the carbon. So we're adding in our nucleophile. The pair of electrons in the bond get repelled towards the oxygen here. We then end up with an intermediate with the nucleophile attached to the acyl chloride. And there's our chlorine on there. So we now have our amine attached. We have the positive nitrogen. This intermediate will then go off and form our final product because the lone pair of electrons here on the oxygen reform the double bond. The chlorine is eliminated. The hydrogen is also removed to make hydrogen chloride. And then our final product is going to be a secondary amide, a secondary amide. So we end up with CH3CO. And then the amide is formed from the nitrogen, one of the hydrogens that's still attached, and the CH3 here. So our product here is N-methyl for the side group, so N-methyl ethanamide. Okay, there's an E on the end here. I'll just move this across. So you can see, so N-methyl ethanamide. And then we will also produce the hydrogen chloride as well. So the hydrogen's eliminated with the chlorine, so that's hydrogen chloride. And remember, if we bring it all together, we've started off here with a base. So we started off with our primary amine. our primary amine reacting with our hydrochloric acid, or hydrogen chloride, sorry, not hydrochloric acid. So our primary amine reacting with the HCl, we end up producing a salt from this part and the hydrogen here, and then the chlorine here is going to be our product as well. So that's looking at the reaction mechanisms of acyl chlorides. Thank you for watching. Make sure that you like and subscribe all these videos. Please make sure you share. It really helps to get these videos out there.